Where did you get x plus y from?
I just made it up. So converting from xy to r theta.
R cosine theta plus R sine theta.
Yeah. So r cosine theta plus sine theta. Then don't forget the r, dr d theta. All right. So now we can start evaluating this. Our inner integral is with respect to r. But here we have this factor here, cosine plus sine. That just depends on theta, so we can factor it out. We can move it outside the inner integral. So we have pi over 2, 3 pi over 2. I'm moving a cosine theta plus sine theta out here. And then all we have left is the integral from, forgot the 1 to 2 of r squared dr. So that's our inner integral, d theta. So there's not going to be much to this one. So here we're going to get r cubed over 3 from 1 to 2, which is going to be what?
In your notes, you got that it transforms into r cosine theta plus r sine theta dA.
Yes, because in the notes I did not pull out the cosine plus sine. I just left it in there, but since we're integrating with respect to r, it's a constant.
Okay.
Yeah. So so it's not actually going to affect the result. It's just going to, if we left it in there like it did in the notes, it's going to sit there and do nothing. We would do the anti-differentiation with respect to r, and still get this r cubed over 3.
So here you're simplifying from what you have.
Yes, actually, yes, because we don't have to worry about theta till later. So we just pull it out. All right. So we plug in our limits, and what you get is 7/3. So now we have the integral from pi over 2 to 3 pi over 2. 7/3 cosine theta plus sine theta d theta. The 7/3, that's a constant, so we can pull that out as well. Okay. So right now it should be in sync with what's in the notes. So now we're just evaluating a single integral. So we're going to get 7/3 sine theta minus cosine theta evaluated at pi over 2 and 3 pi over 2. So when you plug in the limits, you'll get minus 14/3. So the main thing here is the setup. You have your function of x and y, so use x equals r cosine theta, y equals r sine theta to convert the function itself to polar coordinates. Include the extra factor of r along with your dr and d theta. And after you define your region in terms of polar coordinates, what are the limits on r? What are the limits on theta? Now, if converting this region, the key is the region itself. If the region itself does not convert well to polar coordinates, if you get something that isn't really convenient to work with, then maybe you're better off sticking with x and y.
We ended up with a...
It's a cone. Defined by this equation, z is equal to the square root of x squared plus y squared. And then we have a sphere on top of that. All right, this is not a very good sphere. All right. So the sphere is defined by the equation x squared plus y squared plus z squared is equal to 8. All right. Now this cone, it's not really conveyed by the picture, but the cone extends infinitely up. So at some point, the cone intersects with the sphere. So what we get is a solid in between. So it has a circular top. The lower portion of it is cone-shaped. So what we want to do, it's the volume of this solid that we want to compute. So we need to take the difference between this height and the height given by the cone. So that's what we're actually going to be integrating over the appropriate region in polar coordinates. Now, if we were to write these equations in terms of polar coordinates, what would they look like? But then it simplifies. I'm going to think in terms of not just how you write x, y in terms of r theta, but how you go the other way.
Would it just be R?
It would just be 2r.
Yeah, z is just r. Yeah. And what about the other? Yeah, r squared plus z squared equal to 8. So we can just write this as z as, so we're taking the positive square root, 8 minus r squared. Okay. All right, so within this solid, it's a sphere that defines the top portion of the solid, and the cone defines the bottom portion. So we're going to integrate square root of 8 minus r squared minus r dr d theta. But what we haven't figured out yet is how do we define the appropriate region to integrate over. Now, I'm going to add a little something to this. Well, actually, all right. In the notes, I restrict this not to the entire portion, like going all the way around the circle, but just from 0 to pi over 4. So we cut it off right here. So it's just this portion. So really 1/8 of this solid that I've shaded in here is what we're going to get. So because the solid is bounded by these surfaces, and the solid is also bounded by these surfaces, y equals x and y equals 0. And we're prescribing that the solid lies in the first octant, where x, y, z are all non-negative. So we could use this to figure out what the limits in theta should be. Because if we look at the xy plane, here's y equals 0, here's y equals x. So what angles would that correspond to if we just want this portion in between?
0 pi over 4.
Yeah, 0 and pi over 4. So this is theta equals 0, theta equal pi over 4. Okay. So we're just taking a portion of the solid that's between these two surfaces, so it's like we're cutting off a wedge. So that gives us our limits in theta. But what remains is the limits in terms of r. So we have to be careful about that. We know that we're starting with r equals 0. But we have to be mindful of when this surface and this surface intersect. So what we can do is we can find out at what r these surfaces intersect. We'll see when they're equal to each other. So we have r is equal to the square root of 8 minus r squared. Square both sides. So now we have 2r squared is equal to 8. So r is equal to 2. So right here,